Hello, everyone. Okay, let me share my screen. Where is it? Ah, here. Okay, so let's see. I guess we are next to the last mile, right? Let me just see. Where we are at the moment. So I suggest let us start by looking through the 2020 final so that you get a accurate idea what you will be expected to do. So the first problem asks you, by the way, the solutions are on the web. I emailed the link to the solutions. You can find them on the web page also. So you have to compute the probability that the skip list with n elements has at least log n squared many levels, right? So this is really easy to do if you understood what a skip list is. And I even give you here in the solution that on page 8 of the lecture slides on skip lists, we computed, excuse me, that expected number of elements on level I of a skip list, denoted by E sharp I, is given by n divided by 2 to the I. And you remember that's because probability that you have a link of level I is equal to the probability that you get I many consecutive tails, right? At least I many consecutive tails, and probability of this is of course 1/2 to the I, and you have n elements. For each probability is 1/2 to the power I, so then the expected number of all elements on level I is n divided by 2 to the I, okay? So we can now apply the Markov inequality to the probability that the number of elements on level I is bigger or equal than 1. What does this mean? That's precisely to say that level I is non-empty because it has at least one element. So by Markov inequality, probability that sharp I is bigger than 1 is expected number of sharp I divided by the bound, in this case 1, and the expected number we just saw is n divided by 2 to the I. And now you just substitute I by log n squared. So you have that the number of elements on level log 2n squared is bigger or equal than 1, so the level is non-empty, is smaller or equal than the expected number divided by 1. So this is n divided by 2 to the, and instead of I, we substitute log 2n squared. And now you can put, you can distribute the logs, right? You put 2 to the power log 2n, and then the whole thing to the power log 2n. And this in the bracket is, of course, just n. So this is n to the log 2n. And then you can cancel out 1 power of n, and you get that this is 1 over n to the power log 2n minus 1. And that's the final answer, right? So you might expect to see something like that, I might take one piece of a derivation of the runtime of a randomized algorithm and ask you to evaluate something specific. And if you understand, you just have to be able to find in your lecture notes where such a calculation occurs, right? And understand the calculation so that you can make it specific for a particular request, right? Okay, so that's the first problem. The second problem is a bit trickier, right? And it's what we started to do last time. So it asks you, assume that that in the deterministic algorithm for ordered statistics, right, that we split all the numbers into groups of 2k plus 1 many elements, right? So in particular, what we did in class is for k equals to 2, because that produces 2 times 2 plus 1 in groups of 5 many elements, right? And we also saw for k equals to 3, when this gives 7 elements and so forth. And here you are asked to derive an estimate of the runtime of the algorithm for general k, and to show that this runtime satisfies that it is always smaller or equal than 10 times ck times n, whatever, for all k bigger or equal than 1, and also to show that for k equals to 1, the algorithm breaks down. So let us see how we do that. And here is, I prepared a nice picture for you. So this is, so all the elements are grouped into groups that have 2k plus 1 many elements, right? Of course, the very last column might be only partially filled, but this doesn't change the analysis significantly, okay? So if you have a 2k plus 1 many elements here, then the number of columns is n divided by 2k plus 1, right? Because every column has 2k plus 1 many elements. So we are now considering the row in the center, right? How many, if you have 2k plus 1 elements, you have k above and please plus that row. So in this rectangle, right, its height is k plus 1, right? K elements on top plus 1 in the middle row. So it's k plus 1, and the size of the rectangle is n divided by 2 times 2k plus 1, right? Because it's 1/2 of the total number of elements. And now everything is really simple. First, we call recursively our algorithm to the middle row, right? The middle row has n divided by 2k plus 1 many elements. So to find the median, this will cost you, it will cost you t of n divided by 2k plus 1 many elements, right? So this is the cost of finding the median. And now what you do, once you find the median, and the median is this orange element that you see here, right, in the center. And now, sorry, I forgot to tell you, first we sort each column by brute force, right? You can use any algorithm. Every column can be sorted because it has only fixed number 2k plus 1 many elements, and k is fixed parameter of the algorithm. Right, so you can sort every column in, say, increasing way going towards the bottom, right? So you can assume that all of the guys are sorted like this. And of course, every column can be done in constant time, which depends on k, but it is constant, right? And there are less than, of course, n many columns. So the whole splitting and sorting column-wise can be done in linear time. Now, once we find the pivot, notice, so all the elements in the middle row, we can permute now the columns using the central element as a pivot, right? So we always compare each element in the central row with the pivot, and if it's smaller than the pivot, we put this column to the left. If it's larger than the pivot, we put this column to the right, right? And in this way, we know that all the elements, so the elements on the left are not sorted, right? But they're all smaller than the pivot, okay? And all elements on top in this pink box, top left corner, they're all smaller than the pivot. Why? Well, every element is smaller than the next element, and it is smaller than the element in the center, right? And the center element is smaller than the pivot, right? Because we we split the columns according to the size of the central element. So every element in this top box is smaller or equal than the pivot, and every element in the right bottom box is larger or equal than the pivot. But let's see how many elements we have in each of these two boxes. Well, the side is n divided by 2 times 2k plus 1, and the vertical side is k plus 1. So each of the boxes contains at least this many elements. But this means that the rest, right? So if you use now this very same pivot to split just the original array without looking at this picture, right? If you split the original array using the orange element as the pivot, right? Then we are guaranteed that each side, both side of the smaller and side of the larger, will have at least this many elements, right? N times k plus 1 divided by 2 times k plus 1, which means that the remaining part has at most, so it has smaller or equal than n minus n times k plus 1 divided by 2 times 2k plus 1, right? And so you now recursively, after you split the array, you now see whether the ith element that you are looking for is on the left or it's on the right. In any case, right, the side, right, notice this guy here is smaller than n over 2, right? And this guy is actually bigger than n over 2. So either side will have at most this many elements. And now you can just do very simple algebra, right? That so calling recursively the algorithm to one side of the partition will take at most this amount of time. And now you can put this under the common denominator, and you get that this is exactly this fraction here, n times 3k plus 1 divided by 2 times 2k plus 1. So the recursion, so the total runtime of our algorithm is small for n elements, is smaller or equal than the runtime of our algorithm for n divided by 2k plus 1 many elements. That was to find pivot, a good pivot, right? And this is operating on one side of partition. We don't know where exactly you will operate. Maybe you will operate on the smaller side, which is this, or the larger side, which is this fraction here. But in any case, this is smaller than or equal than this. And so this is the recursive call on one side of the partition. And this is, of course, the overhead of splitting the elements in the groups into the groups of 2k plus 1 many elements and sorting by hand. So it's certain constant c that depends, of course, on k, but it's a fixed constant times n. Okay. Now we have to figure out, we want to show that T of n is smaller than some k times ck times n, right? Because we want to show that it is linear time algorithm. So we want to figure out this capital K, how large it has to be so that you always have this bound, right? Well, you will use this bound to prove, you will prove this bound by induction. So you will assume that the bound works for n divided by 2k plus 1, because this is, of course, smaller than n, and this is also smaller than n. So you are assuming that this guy here, right, this guy here is smaller or equal than this, and this guy here is smaller or equal than that, right? And this should, and k should be such that the sum is smaller or equal than k times ck times n, right? Because that's the bound that you need. So you can divide by n times ck, and you get the following inequality, right? And then you can just do algebraic mumbo jumbo to reduce it to a little bit simpler form, which is this form, oops, this form here, right? And you can now multiply and put all capital K's on the left and all small k's on the right, and you get that this inequality, it's easy, it was just plain algebra that reduces to k bigger to 4k plus 2 divided by k minus 1. And so if you take k that is bigger or equal than this, any number bigger or equal than this, and you can in fact take capital K to be equal to 4k plus 2 divided by small k minus 1, right? The claim is then that the runtime of your algorithm will satisfy this inequality because right, this guy here is replacing capital K, right? And lo and behold, it's easy to see, to prove this by induction, right? So we consider, so this is our runtime, right? And we assume that by induction, this is smaller than K times CK times, and then, so this is our size of the input, right? So this will be by induction hypothesis smaller or equal than 4k plus 2 over k minus 1. This is our k times ck times, and n here is n divided by 2k plus 1. And this guy here, right, is by induction hypothesis smaller or equal than, let me, is smaller or equal than 2k plus 2. Sorry, it's not 2k, it's what is our, it's 4k plus 2 here. And it's 4k plus 2 divided by k minus 1 times ck, and then the fraction is 3k plus 1 divided by 2 times 2k plus 1, and then this times n. And if you substitute this, in the equation, this is what you get, right? This is what we just derived. We derived this inequality, right? That's, oh, I forgot to add, sorry, here I have to add plus ck times n for the overhead, right? And I forgot here n plus ck plus times n. Okay, so I should correct that in the solutions. This is what we have here, right? This is the part that we just derived. And then you can take ck times n outside, and you get this algebraic expression that it's easy to see by basic algebra. It simplifies just to this, but notice this is precisely our capital K. So lo and behold, we have proven that the runtime of our algorithm, right? Because we know that the runtime of our algorithm is smaller or equal, so T of n is smaller than this expression, and lo and behold, then we get that Tn is smaller or equal than this, and that's precisely our capital K. So by induction, we conclude that this works for all n. Now notice, for this to make sense, K has to be bigger than 1, right? Because otherwise you get 0 on the bottom. So you can suspect that the things break down if K is equal to 1. And lo and behold, if you consider the condition that we had, which condition? This condition here, right? If you look at this condition here, if you substitute k is equal to 1, what do you get? If you substitute that k is equal to 1, you get k plus k4 divided by 2 plus 2 plus 1 has to be smaller than 3k, right? This is obtained from previous inequality, just substituting k is equal to 1. And you get that this is what you have to show is that 3k plus 3 is smaller or equal than 3k. But this, of course, doesn't work for any capital K because left-hand side is always larger. So you have to split into at least 5 many groups of at least 5 many elements, right? So this is kind of, this was probably the hardest problem on the final, but the vast majority of people actually solved it. I wasn't terribly picky if you made an algebraic mistake for as long as I saw that you know how the bounds work and where they are obtained from. Okay, any questions so far? Okay, if you don't have any questions, we can move to problem number 3. So assume that you draw independently and uniformly, randomly n points, x1 up to xn, from a unit ball in n-dimensional space Rn. So notice this is a little bit different because we draw usually much fewer number of points than the dimension of the space. The dimension of the space is usually d, number of points is n, and usually n is smaller than the dimension, but not necessarily, right? So here we are drawing exactly the same number of points as the dimension of the space, and we do that from the unit ball, right? So we have to show that with probability of at least 1 minus 1 over n, so very large probability, the sum of the lengths of the corresponding vectors satisfies that it is smaller than n and larger or equal than n minus 2 log n. So, of course, this sum is smaller than n because all the points are drawn uniformly from the unit sphere because they are inside the sphere. The length of each vector is smaller or equal than 1. So their sum is, of course, smaller or equal than n. But of course, the tricky part is to show that this sum is very unlikely to be small, namely it's always bigger than n minus 2 times log n. And notice 2 times log n is minusculous compared to n, right? So this sum will always be very close to n. And again, you have explicitly that on the page 13 of the lecture slides on Johnson-Lindenstrass, we prove that if we draw independently and uniformly n points, right, x1 to xn from the unit ball, right, of dimension d, and if epsilon is any number between 0 and 1, then the probability that the length of this randomly drawn vector will be smaller than 1 minus epsilon satisfies, right? So this probability satisfies that it is smaller or equal than e to the minus epsilon d, all right? Now, in our case, d will be equal to n, but we can keep it as d so far. And you take epsilon equals 2 ln n divided by d, as we did this in the, this is all in the slides. And we obtain that for each I, probability that the length of the vector is smaller than 1 minus 2 ln divided by d is smaller than 1 over n squared. And you can now just instantiate d equals to n, right? And you can obtain that probability that each of xi is smaller than 1 minus 2 ln n divided by n is smaller than n times, because you have n points, and for each of them the probability to be smaller than this is smaller than 1 over n squared. So by the union bound we conclude that the probability that at least one drops below this bound is smaller than n times probability for each of them, so it's n times 1 over n squared, which is equal to 1 over n. So consequently, with probability of at least 1 minus 1 over n, we have that each of them satisfy inequality that length of xi is bigger than 1 minus 2 log n over n. So if you sum the left-hand side, the right-hand side becomes n minus, and then n times this is just 2 ln n. And so we get the desired bound that with probability of at least 1 minus 1 over n, you get that n is, that the sum is between n and n minus 2 ln n. So that's the third problem. So what is here? I simply test you whether you understood how we find probabilities that randomly picking vectors uniformly from the unit sphere, right? That you have this probability estimate. And in fact, this probability estimate is trivial to obtain, because what does it mean that this is smaller than 1 minus epsilon? This means that xi belongs to a sphere of radius y minus epsilon. So probability that this is inside this sphere is the volume of that sphere divided by the volume of the entire unit sphere. But the volume of sphere of radius y minus epsilon in d-dimensional space is the volume of the unit sphere times 1 minus epsilon to the power d. So now you can cancel out the volume of the unit sphere on top and the bottom, and you get just 1 minus epsilon to the d. And then this is, and it is in the notes, it's a very important inequality often used in randomized algorithms, that 1 minus epsilon to the d is smaller than epsilon to the minus, smaller than e to the power minus epsilon times d, right? So really just basic understanding of the geometry in high dimensional space. So if you understand the lecture notes, solving a problem like this will take you just a few minutes. Okay, so this is about high dimensional space. Now, an example of a Markov chain. Okay, so here is the problem. So you happen to be a very good student, receiving only distinctions and high distinctions. To get a high distinction, you need to to have a score between 85 and 100, and to receive a distinction, you have to score between 75 and 84. Okay, and now you are lazy to compute your VAM and you will prefer to estimate it. So you noticed that on average, after each high distinction, you get, let me see, after each high distinction, in the next exam, you received another high distinction twice out of every 3 times, right? And after each distinction, you are equally likely to get a high distinction as you are likely to get distinction. And you also notice that whenever you get a distinction, all scores between 75 and 84 are equally likely. And similarly, whenever you get a high distinction, it is equally likely that you got any score, every score between 85 and 100. And using this data, you want to estimate your VAM, your average mark. And this is just a simple Markov chain with the states distinction and high distinction. And we are given the probability that a high distinction is followed by another high distinction to be 2/3. So probability of the Markov chain to transition from high distinction again into the same high distinction state is 2/3. But this implies that probability to transition from high distinction into distinction is only 1/3, right? And you are also given that the probability to transition from distinction to another distinction is 1/2, and this of course implies the probability that a distinction is followed by a high distinction is 1/2. So does the frequency HD of your high distinctions and the frequency of your distinctions, right? The probabilities of you getting high distinction and probability that you get a distinction satisfy the following property, right? These are the global probabilities, right? And they have to be preserved through these transitions, right? Because this is a stationary distribution, because it corresponds to overall probability, right? At any moment in time. So from this matrix equation, right, you can obtain 3 equalities, right? Only 2 of which are independent. First of all, because you either get a distinction or high distinction, D plus HD is equal to 1, right? The probabilities of only 2 possible states must add up to 1. And then you have that D times 1/2 plus HD times 1/3 is equal to D, right? Here it is. And similarly, D times 1/2 plus HD times 2/3 is equal to HD. And now from the first 2, or first and the third, this doesn't really matter, equations, it's easy to see that the solutions to these equations are D is equal to 2/5 and HD equals 3/5. But now you also, so these are global probabilities for you to get a distinction and the probability to get high distinction. And you then use the feature that whenever you have a high distinction, all scores between 85 and 100 are equally likely. So the average score is 92.5. And similarly, whenever you get a distinction, all scores between 75 and 84 are equally likely. So the average score is 79.5. So the best estimate of your WAM is given by the average score for HD times probability to get HD plus the average score for D times probability to get a D. And lo and behold, when you compute this expression, you get that your WAM is 87.3. Right, so it's a typical, typical problem involving Markov chains, and I'm just testing you that you understand how stationary distributions for the states and the transition probabilities, how they are connected, right? So that's problem number 4. You can see it's so far, maybe one with the deterministic algorithm for order statistics was a little bit trickier. But if you understood the case when you split them into groups of 5, the rest is just simple algebra. Okay, that's a best place to now make a 10-minute short break, and then we will do the remaining 2 problems. So just 10-minute break. Okay, time to do the finishing touches, right? So here is another problem that is sort of typical of what I can ask you to do. So it's just checking that you understood and can apply PageRank correctly. So use the PageRank algorithm to rank Twitter users according to their popularity. If a person A follows person B is important to person A, proportionally to the number of times A retweets messages of person B plus the number of times person A liked messages of person B. So how would you turn this into a PageRank problem? Well, that's very simple. The vertices of the graph will be the Twitter users, and there exists a directed edge from a user A to user B, just in case user A has retweeted messages of user B, and a person A liked messages of user B. So the weight, let's call it W star AB of edge from A to B, is the ratio between retweets, a number of times A retweeted a message from B, plus the number of times A liked a tweet of person B, divided by the total number of retweets of user A, plus the total number of likes of A of any user U, right? So retweet of any user and likes of any user. And this ratio is the weight of the edge AB, right? And now then you have to resolve the problem of dangling nodes, and you do that by assuming that by giving to each user, you give this user he likes any other user with a very small weight W that is equal to 1 minus alpha divided by total number of users. This alpha here plays the role of a random teleportation of the original page rank. Of course, here it doesn't have this interpretation. It's a just technical gadget to make sure that the underlying graph will be both fully connected and aperiodic, right? And then you have to make sure, right? So this takes care of dangling nodes, and alpha is usually 0.85, right? But now you have to adjust all the weights by multiplying the original weight defined through this ratio, right? By this coefficient alpha 0.85 or so. And then you have to add to that the factor 1 minus alpha divided by u. That would be the probability in PageRank. This was the probability of a user to jump directly to another web page. Here you don't have this nice intuition. Here it's only a technical gizmo to make sure that the graph is fully connected and aperiodic. Maybe try to think how you could interpret this. Maybe every user likes every other user, even that he doesn't know the person. You leave a possibility. So everyone likes everyone at least a tiny little bit. Yeah, I don't know if one can give a better interpretation. It's really a technical gadget to ensure existence and uniqueness of the stationary distribution of the underlying Markov chain. And remember, we had a similar example when you have a collection of all papers in a large database, right? You represent all the papers as nodes in a graph, and you put a link from one paper, from paper A to paper B, if and only if paper A cites paper B, and you can even introduce a weight that would be the number of times paper A cites paper B divided by total number of sites in that paper. So it's all same old, you know, it's really the same tricks, just in different setups. But all of this is extremely useful. You can find on the web page a paper by a former 4121 student, his major project, in which he applied PageRank to the problem of evaluating security in computer security by evaluating the trustfulness of was it servers, and so if you are interested, you can look it up. It's a really nice application of the PageRank. And this, of course, if you know what PageRank is, this takes maybe 10 minutes max to write down the answer. Okay, and the very last problem on that final was to explain in your own words why spectral clustering algorithm works for clusters that are not center-based. And that might have been, actually, to my surprise, this was probably among the hardest problems, even though it's not hard at all. But I guess students were just deterred by complexities of spectral clustering. And how would you explain this? Well, spectral clustering, right, operates on the graph whose vertices corresponds to the points that you want to cluster. And usually these points are represented as vectors, right? And usually they are vectors in a very high dimensional space. And this is a problem, right? We don't like working in high dimensional space. So instead, we collapse the whole system into representing vectors as points, right? And between any two vertices, right? Between any 2 points, there is a link, right? Of weight. So a non-directed edge in that graph of weight proportional to the proximity, or more generally, similarity of these two vectors. So similarity measure depends inversely on the distance between points. So excuse me. And the most common measure of similarity is this Gaussian measure. So the weight of the edge between two vertices I and j is equal E to the power minus, and then the distance between the two vertices squared divided by 2 sigma squared, right? Now, this sigma is design parameter, and if you change it, you might get different clusterings, right? And usually, if you are asking for a relatively large number of clusters, say you want to 9 clusters, then you would put sigma that is small, and if you want just a few clusters, you might want to make sigma a little bit larger. Why? Because in this way you control how quickly the weight between 2 points decays, right? And so you want this sigma to be such that it keeps points in the same cluster together, and it's small for points in different clusters. So so informally speaking, right, spectral clustering attempts to break up the points into clusters such that points which are close together, sufficiently similar, stay in the same cluster, right? The clusters are essentially approximate connected components. So this is the idea. If this is one cluster and doesn't have to be center-based, and this is another cluster, and this is also another cluster, then you want that between any 2 points you can walk through edges that are all with large weights, right? And whenever you have 2 points that are in different clusters and you try to walk from one to the other, at least one edge will have a low weight, right? So in that sense, this is just finding approximate connected components, things that are accessible, where points remain accessible from one to another through significant edges, but you cannot cross to another cluster using a path that has high weights, right? At least one link has to have a low weight. So the clusters, being such connected components, do not have to be center-based, right? So you might have a cluster that looks like this, right? 2 clusters. And then you see the idea here is that even though between this point and that point, the distance is very large, but you can walk from one point to the other point, always using only edges with high weight, because they all connect points that are in high proximity with each other, right? But to walk from here to here, you would need the distance will be much larger than the distance in this cloud, or at least you hope so. All right. So, and this would be really the full answer. And as you can see, it's all really what it just involves reading your lecture notes and understanding what is being done there. And then it will be piece of cake to, as I say, either to tweak a little bit the algorithm, or to maybe generalize it in some way or apply it in some way. But we will stick very close to your lecture notes, and I promise there will be no tricky questions where you have to figure out something, some kind of very creative way. I want to just make sure that you studied these algorithms and understood them and appreciated the design techniques that are used to design these algorithms. If you are mathematically minded, then of course I would expect you to read every single detail and understand all the derivations, right? But if you are not mathematically minded, it's enough to understand clearly the techniques and basic steps of the design, and you have absolutely nothing to worry about. Okay, let me see, I have questions. Oh, sorry, you can, oh gosh. You should have unmuted yourself. So let me now share my screen with you. I am really getting senile. I didn't see. So here it is. So what I was telling you is, I'll just very quickly repeat what I have said. So this is the usual way how the weight decreases with the distance. Oh, I'm really awfully sorry. Oh gosh, you were for 8 minutes. You were blind. So please feel free to unmute yourself. And well, now it's the last time, so too late for you. I'm really sorry. So this is how the weights for the graph, right? You have vectors, and you can compute the distances between points, which would be, so what is the distance? It's square root of sum I equals from 1 to the number of dimensions. So let me use capital D here. To the dimensions of xi, point xi, coordinate D minus point y, point, well, let's not use indices here. So the distance is sum of x I minus yi squared, whatever the dimension is, which can be very large, and then square root of this. So that's the distance. And usually we denote this. This is essentially the length of the difference vector. So this is simply the norm of ai minus aj squared, right? And this sigma controls how quickly the weight decays as the top increases, right? You have to choose this parameter carefully so that the weights remain reasonably high for the points that are in relative proximity to each other, so that the whole graph doesn't break up into too many pieces, right? And so how do we explain spectral clustering? The clusters are approximate connected components. What does this mean? It means that for any 2 points in the same cluster, you can walk from one to the other using only edges that are with high weight. But if you have 2 points that are in different clusters, right, then you cannot walk from one to the other using only edges of high weights. At least one of the weights, right? At least one of the weights. Now I cannot erase this, but that's okay. At least one of the weights has to be, just ignore this point in the middle, has to be small. And so spectral clustering is trying to break up this graph, right? So that the clusters are approximately connected components of the graph. And lo and behold, that's all what was for this exam. So just, you know, there is, I don't think I can show you more important examples. You have the practice problems with solutions, so you might want to read it. Also, all these solutions to these problems, very, very detailed, are on the web. So I urge you to read them very carefully and make sure you understand everything. And above all, read very carefully the lecture notes and make sure that you understand every single step. You can ask me as many questions as you want. I will have office hours tonight, right? From 5 to 6, and I'll have office hours on Monday, Tuesday, Wednesday, and Thursday. On Friday is your exam, so I'll have 5 to 6 or as much as you need. If I have lots of students asking questions, if I have to stay until until I don't know what time, right? 8 o'clock or 10 o'clock, I'll stay. But you can ask me as many questions as you want. Yeah, well, that's all what I prepared for this class. I really hope, please do my experience. Every year, I really, really agonize about the content by trying to balance it to cover everything that is truly important in modern, especially data science and machine learning algorithms, and on the other hand, to make it palatable for you to want to learn it. So please give me feedback, what you liked and what you didn't like about the course, and how I should change it for next year, because I really care about that. Okie dokie, so we can finish today early and study hard until Friday, and don't hesitate to ask me any questions that you might have. You can also email and use the forum, and I'll see you hopefully on my office hours. If not, then good luck on your final. I will email the problems and post them on the class website, and you have to email me your solutions 3 hours later, right? And if you have one of these special provisions, you can take whatever number of minutes you are entitled per each hour. I think it's usually 15 minutes. So you can have 45 extra minutes to email me back your finals. Any questions that I might answer now regarding the final? Okay, if not, then feel free to come to my office hours. They are not recorded, so if you feel shy to ask, it will stay between us, right? So I'll see you tonight and on Monday to Thursday next week. You're most welcome. Please do remember, only one person did my experience, and head of school wants to hang me for that. The school wants to hear your voice. So please do it. You're most welcome, and best of luck in your future endeavors. Okie dokie. Bye now. You're really, really welcome. I really hope you found the material useful. Cheers.